In this video, I want to have a look at another method of approximating the root of a polynomial. This one is called Newton's method. So let's have a look at how it works, and then we'll get into the technical side of things. So if we have a look at this function here, we'll call it f of x. We want to find where this root is. With Newton's method, we're going to start with an approximation. So we might have this value here, call it x1, and we know that x1 is close to this root, and we'll talk about what that means to be close enough to it that we can use Newton's method in just a minute. But we know that x1 is close to the root, but we want to get a better approximation. So what we're going to do is we're going to draw a tangent to this function at this value of x1. So we've got our value here, so we're going to draw a tangent at this point. So that's going to be, and it's going to be a bit dodgy drawing it on here, but as best we can, coming down this direction. All right, so we've got this tangent drawn to the curve at the value of x1. So now we're going to find the x-coordinate, the x-intercept of that tangent, and we're going to call that value there, we're going to call it x2. Then we're going to do the same thing again. So that's our first iteration. If we want to get even closer, we're going to find the value of the function at that point, and we're going to draw in a tangent at this point now. We draw that in there. You can see it's gotten closer again, and we could keep doing that, and every time we do it, this one would be called x3. I can't draw it in there, but that would be x3. Every time we do it, it's getting closer and closer and closer to what that actual root is. So the difference between Newton's method and the bisection method, Newton's method, if it works, if we've got a value that's close enough to start with, then it's usually faster and more accurate than the bisection method. So you do less iterations to get a closer approximation. But there are times when Newton's method won't work as well. And that's if we don't start close enough to the root. So for example, if we had something that looked like this, if we're trying to find the value of this root here, but we start with this x1 here, so we're starting with this value. If we were to draw a tangent at that point, we're just going to get a horizontal line. So that's not going to get us any closer to that point at all. So that one won't work. Or if you go on the other side, say we're trying to find this root here, and our x1 is too far over here, then we're just going to take off in the other direction. We're not going to get closer to our root at all. If we write out the process for Newton's method, we're going to suppose x1 is close to a root of the equation f of x is equal to 0. Then we want to find the equation of the tangent at that point. So the equation of the tangent to f of x at x1 is this thing here. So we've got y minus f of x1 equals f dash x1, x minus x1. And this might look a bit confusing to start with, but all it really is what you're familiar with, is your y minus y1 equals m outside of x minus x1. So our y1, we've just written it as f of x1, it's the value of the function at x1. Our x1's the same, and our m is our gradient. So we know that the gradient is the value of the first derivative at that point. So we're saying we find the derivative and substitute it in, and that's going to give us our m. So we're going to find the equation of that, and then we need to find the x-intercept of that tangent. So the x-intercept of the tangent is going to be given by x is equal to x1 minus f of x1 over f dash x1. And that value is going to become our next approximation, which is our x2. So we could write x2 here instead. Now again, this looks a little bit complicated, but all it is rearranging this. So to find the x-intercept, we know that we set y equal to 0. So from this line here, that would give us minus f of x1 is equal to f dash x1 outside of x minus x1. Now we want to get this x on its own, so we're going to divide both sides by this f dash x1. So we're going to have f of x1 over f dash x1 equals x minus x1. And then we're going to add that x1 to both sides. So we're going to have x1 minus f of x1 over f dash x1 is equal to x. So that is our x-intercept. And like we said, we're going to call that x-intercept x2. And then if we do a second iteration, it'll be x3. So the example that we're going to have a look at is the same example we used in the bisection method video. So we're told the equation x cubed plus x squared plus x minus 5 equals 0. has a root near x equals 1, and we're asked to use two applications of Newton's method to find an approximation for the root. So we actually don't have to find the equation of the tangent, we just need to know what its x-intercept is going to be. So we know that that's going to have the form, if this is x1, then x2, the x-intercept of that tangent, is going to have the form x1 minus f of x1 over f dash x1. So to find x2, we're going to have to find all three of these values and substitute into this formula. So we know that x1 is 1. We can say that f of x1 would be 1 cubed plus 1 squared plus 1 minus 5, which will give us minus 2. And then we need to find f dash x1. Should really just put a 1 there, shouldn't we? So f of x is equal to x cubed plus x squared plus x minus 5. If we differentiate that, that would give us 3x squared plus 2x plus 1. So that means that f dash of 1, we can substitute that in there, so we'd have 3 times 1 squared plus 2 times 1 plus 1, which would give us 6. So these are the three values that we're going to use in here to find x2. So x2 is going to be 1 minus 2 over 6, which will give us 4 over 3. So that's our first approximation, but we want to use two applications. So then we're going to find x3. So to find x3, we need to know x2. So we know that x2 is 4 over 3. We need to find f of x2. So that's going to be 4 over 3 cubed plus 4 over 3 squared plus 4 over 3 minus 5, which is going to give us 13 over 27. Then we need to find f dash x2, and that's going to give us 3 times 4 over 3 squared plus 2 times 4 over 3 plus 1, and that's going to give us 9. So then these are our three values that we're going to use to find x3. So x3 would be 4 over 3, which is x2, minus f of x2, which is the 13 over 27 over 9. And if we pop that in, it's going to give us 311 over 243, which is approximately equal to 1.2798, and it keeps going on. So this is our approximation of where that root is. Now, when we did this example using the bisection method, we said that our root was somewhere between 1.25 and 1.5, and it was probably closer to 1.25, but that's as accurate as we could get only using two applications. Using two applications of Newton's method has gotten us a lot closer. It's given us 1.2798. If we would actually find in other ways the exact root of this polynomial, and it'd come out to be 1.2782, and the number continues. So you can see that this one is a better approximation for the same number of iterations. So let's have a look at Newton's method for approximating roots.